So you think you know what time it is. So we're going to talk about a little history of timekeeping and frequency measurement, really more emphasis on the measurement of time. And it's kind of a fascinating thing that's always interested me through my career in engineering. I worked with some precision timing systems for satellite operations back in the day when I was still working. So some of this stuff that comes up as an introduction, have you ever wondered where the hour came from? Why do we have hours? Why do we have minutes and seconds? Where did they come from? And what time really is it? Do we really care? Do I care what time it is? Well, there are some reasons for caring what time it is, but there's some interesting things that you'll find as we go forward through this. So those answers are straight ahead. Okay, I'm going to let this settle here for a second or two and let you guys read that. You've probably heard that many times. I love that. That's why you got to have three. This one is great. I love that. Yeah, that's a great quote. But anyway, well, let's talk a little bit about the history of timekeeping. So as you know, early man, they watched, as we do, we watch the sun and the moon and the stars, and they observed that there were cycles that they followed, and they followed seasons. And so with the seasons, they could plant crops. And of course, there were religious observations made through this. And it really was the beginnings of what we call astronomy today, as the ancients watched the heavens and watched the stars and the planets and all that, not knowing what the planets were at that time. But they were watching the skies, and they knew that the seasons coincided with the movement of the sun and the movement of the stars in the sky and all of that. So some of the earliest attempts at timekeeping started in Egypt about 3500 BC with an obelisk. The obelisk is just a stone tower, right? And this was able to indicate morning and afternoon, and it was able to indicate the shortest and longest days of the year. And they could make marks. So this is kind of like a sundial. They made marks that would show hours. So this is where hours comes from. We know where that word originated is from Egyptian timekeeping. And it wasn't until sometime later, roughly 2,000 years later, at 1500 BC, that somebody actually came up with the idea of a sundial or a sun clock, where you could actually keep track of the time. This was considered one of the first portable timepieces. I don't know if I'd want to wear one of those on my wrist or not, but they are fairly portable. And the sundial will give you 10 hours plus 2 hours of evening twilight. So that's a good thing to know about. Well, the next thing to come along was a mercat. And this was one of the earliest astronomical tools from around 600 BC, earliest known astronomical tool. And I was trying to find a decent photograph of this and explain it, but it's basically a horizontal bar and a plumb line. And you could tell time at night by the transit of certain stars. That was the idea of this. So as transit, as the Earth is rotating, your sky is changing around the pole. And so transit is when they're directly over, in the directly overhead meridian. And that's your transit when the star passes through there. And you could tell what time it was from that. So interesting. And of course, this added 12 hours of night. So this also explains where we got 24 hours from: 10 hours of daylight, 2 hours of evening twilight, and 12 hours of nighttime. So the Egyptians, we owe that to the Egyptians. So some other early timekeepers. The water clock, around 1500 BC. Amenhotep I, during his reign, they came up with this device, and basically it measures time by the flow of water. And I remember as a science project in like the third grade, I built one of these things out of some kitchen hardware, like a measuring pitcher and punched a hole in it and let the water drip out. And the pitcher was marked with time. You could tell time with the thing as the water drained out of the pitcher. Well, this was adopted in 325 BC by the Greeks, and they called it a clepsydra. or translated water thief. Clepsydra is the water clock, and water flow marks the passage of time. And by 100 BC, these things got a lot more elaborate. They could actually use them to work machinery, and so you could actually drive a mechanism which told time. You could see seasons, you could see astronomical data, all from water flowing, which is pretty cool. Still in use today in some parts of the world. So another instrument that came along early on was the thing called an astrolabe. And it's not really a clock, but it's an astronomical instrument. And it's used, you can use it to measure time. You can, from looking at the position of stars and the sun and the planets, you can figure out, if you know where you are, you can figure out what time it is from that. And the principles of this go back over 2,000 years for the astrolabe. And it was first in practical use around 400 AD. And so the uses we talk about are a determination of time of day or night. You know, if you know the position of the sun, you use the astrolabe to figure out what the time is, where you're located. And that's an important concept, local time. We'll talk more about that as we go forward. But you can determine time of day or night. We can determine the sunrise and the sunset and celestial positions with an astrolabe. It's quite a useful instrument. And these are a couple of examples of what they look like. Quite beautiful instruments from 1400 and 1280. So good stuff. So going on, other things that were used to tell time. How about a candle or incense? You could mark the candle or the incense with hours, and as it burned down, it could tell time because it burned it, you hopefully burned at a constant rate. The other one that everyone's familiar with is what's known as a sand glass or an hourglass. These all suffer from poor accuracy, however. And that was a major problem with all of these early clocks, that poor accuracy. But we were about to embark on a revolution. But before we talk about the revolution, let's talk about what really is a clock. And we're going to define what that is. It's a device that has two primary components. And the primary components involve a repetitive processor action. That's the first piece at regular intervals, right? And with that regular action, the repetitive process, you can mark equal increments of time. And of course, the other component of a clock is you have to have the means to keep track of and display the results. So those two things together are what form a clock. So getting into the Renaissance, there was another revolution with timekeeping in Italy with something called a verge folio escapement. And this used mechanical motion to keep that regular interval of time. And so the verge is the rotating shaft, and the folio is the escapement that you see here. Let's see, I should bring up my laser pointer so I can point to this thing. There's the escapement, and the folio is this, and it has a beam with weights on it to maintain, you can adjust the rate at which this thing swings back and forth. So this was an early attempt at keeping more precise intervals. So this is regulated by that escapement. That's the escapement right there. And so this led to the first mechanical clocks in Italy. And the first place they ended up were in clock towers, like in the center of a city, a center of town. 14th century, we started seeing clock towers appearing in Italy. And they would tell the hour. That's all they were really capable of doing at that time, the 14th century. They would tell the hour because they weren't that accurate, but they used a lot of them used weights for power. And these lasted about 300 years before there was another revolution. But because of the mechanical nature of this, they were difficult to regulate. They were subject to friction and temperature changes, and that tended to really mess them up. So it took the Germans to figure this out. The weights were replaced by spring tension in 1500. And so like what we're used to today, we use spring tension in a watch, a mechanical watch or a mechanical clock. We wind up a spring. And this, of course, allows for much smaller size. We don't have to have the big weights like think about a grandfather clock, how that works. This allows a smaller size. However, as the tension changed, so did the rate. So we've still got some problems with this. It's still not that accurate, but it's more accurate than the verge folio system. Um, they were portable. So one of the outcomes of this, they weren't portable like you think of a watch today, but clocks began to appear in homes. So people had their own clock in their home. And of course, what this also led to were the earliest pocket watches. And because it was a bit more accurate than the previous generation, we added the minute hand. We added a minute hand. So that was a big thing. Now I'm going to talk about minutes and seconds and hour. Well, we talked about hours. I haven't talked about minutes and seconds yet. We'll get to that. But what was the next great innovation? Well, it was the pendulum. So the pendulum was created by Galileo of all people, and he's been credited with devising that pendulum clock, but he never built one. He came up with the concept of it, but he never fabricated one, never actually built one. It was Christian Huygens who actually built the first pendulum clock. Now you know his name possibly from other things. You may not know that he's the creator of the or inventor of the first pendulum clock, but he was an astronomer in the 1600s, a very well-known astronomer, and one of Galileo's what would I call him, an adopter of Galileo's telescope. So he observed the planets. He was known for observing Saturn and Saturn's rings, and actually discovered Titan, the moon Titan. That's accredited to Christian Huygens. So he built that first pendulum clock, and amazingly, an error of 1 minute per day. And as it improved, it got down to 10 seconds per day. And later he devised something called the spring balance. And the spring balance is something we use today in mechanical watches and clocks, that spring balance. I've got a picture of one here. Let's see it in a minute or two. The next guy to come along was Robert Hooke. And you may know this name, not from clockmaking, but from microscopes. He came up with something called the anchor escapement. And of course, Robert Hooke is known for the first compound microscope, a lot of inventions that he was credited with. But this anchor escapement is the thing that really changed the way clocks worked. So give you an idea what this hardware, I love this little animation. The Swiss escapement, this is kind of what we were talking about with Hooke. What he developed was this type of an escapement. And of course, the spring balance. And if you've ever looked at a watch, you look at the mechanism of a watch while it's operating, you'll see this thing spinning, it'll back and forth movement of the spring balance. And you can see the spring there in the center. And that is a form of pendulum, if you think about it. And that's how you regulate the rate in a watch or a clock. So next, let's talk about that. Why 60? Where did that come from? That's kind of an odd number for us. We're used to the decimal system, but 60 is an odd one. So let's go back to between 300 and 100 BC in Babylon. In their astronomical calculations in ancient Babylon, they used something called a sexagesimal system, number system. We're used to the decimal system. We know binary. Sexagesimal is base 60. Well, hexadecimal too is base 16. Sexagesimal, base 60. The thing is that 60 is a convenient number. It's divisible by 2, 3, 4, 5, 6, and 10. And so this is an interesting part of it. But the first fractional sexagesimal place is called the minute. So that'd be like in a decimal system, we've got tens and hundreds and thousands. The second fractional sexagesimal place is the second in ancient Babylon. And I'm sorry, I'm ahead of myself. The first fractional sexagesimal place is the minute, and the second fractional sexagesimal place is the second. Yeah, sorry about that. But you get the idea. So that like ones and tens and hundreds. So the first fractional place is a minute. The second fractional place is the second. So this is where we get minutes and seconds from ancient Babylon. Combine that with our 12-hour day from Egypt, and we've got our normal, what we take for granted today. It's like, okay, 24 hours a day, 10 hours a day, 2 hours of twilight, and 12 hours a night. So there you go. That's where it all comes from. Kind of interesting. So next, what is time? Well, good question. And do we care? Yeah, we care. There are three important concepts associated with time. One is the idea of time or date. So this is defines a point in time, like 12:37 p.m., April 23rd, 2004 Pacific Standard Time. That's a time or date. That's a concept of time. That's a specific time. Another way to express that, 299-17-05-23.1. So that's the 299th day of the year at 17 hours, 5 minutes, 23.1 seconds. So that's a time. And the first one is an example of a date in time, but this is just a time. It's relative to something else like January 1st. So the next thing we talk about is time is an interval. So interval is not relative necessarily to anything like a date. And so 1 hour, 2 minutes, 34 seconds, it's a duration or the time of day. There's no reference to date and time. It's just an interval. It's just some quanta of time. The third concept is synchronization, and this becomes really a big deal as we move forward and get into the industrial revolution and start thinking about things on a global scale. Synchronization becomes a big issue, and it took quite a while to get this figured out. But let's talk more about synchronization. You understand what time and date is, you understand what an interval is, but synchronization is the interesting thing. So up to this time, timescales are based on celestial events and mark the passing of days, seasons, years. We've talked about that before. And the time of day is based on the rotation of the Earth. As we began navigating the globe, time became important to navigation, to know where you were. Where am I on this globe? So this idea of synchronization to a common time frame became important. So this is important to navigation. Trade routes opening throughout the world led to accurate time being essential. So this is an important aspect of it. So the trade routes, the other important aspect in the Industrial Revolution were the railroads. Think about it. Railroads, if you're using local time to schedule, local time is based on the position of the sun. So 100 miles east of where you are, the time is different than your location. The local time is different. So if you're trying to run a schedule with railroads, you have a problem because if you've got one track, you've got trains heading towards each other on one track. You need to know what a uniform time scale so that you could have accurate time to be able to schedule your trains. And so this idea of standard time actually came from the railroads. This notion of standard time. The British railroads at the time had troubles with this. Remember, the time is a local thing, as I just described. It's local. We talk about local noon, the local time. That's when the sun is directly overhead, and of course, it's dependent on the seasons and a whole bunch of other things. So it's a problem. So it's difficult to maintain a schedule for a railroad when you've got all these local times. So in 1840, the Great Western Railroad in Great Britain adopted something called Greenwich Mean Time. And this became what is known as British Standard Time and GMT. Now if we've been around long enough, we're familiar with GMT. GMT is unless you live in Greenwich, you don't talk about GMT anymore. We now talk about UTC, and I'm going to talk more about that in a little bit. But GMT is what we used to call it before the transition to the UTC, Coordinated Universal Time. So GMT is based on the Greenwich Observatory. They're the ones that set the standard. And at the time, they were renowned for very accurate timekeeping. And so they set the time standards for the railroads in Great Britain, Greenwich Mean Time. And this is based on what we call now the prime meridian. The prime meridian passes through Greenwich. Okay, so another timekeeper that we may be familiar with, and if you use GPS in any way, shape, or form, you should be familiar with U.S. Naval Observatory. This was established in 1845 in Washington, D.C. And the idea of the Naval Observatory as an accurate timekeeper and tied in with ships and navigation, the term dropping the ball, if you've ever heard this term and ever wondered where that came from, it has to do with what the Naval Observatory did every day at noon. They would drop the ball and you could observe the ball falling from your ship and set your clock. Now, another way to do that, they could use a cannon and a lot of, I got to tell you, when I was living in Hong Kong, the Royal Observatory in Hong Kong fired off a cannon every day at 12 noon. And that's a testament to the past. I mean, this is how the ships lined basically set their chronometers to that time at daily at noon. So that's kind of an interesting little thing, but that's the dropping the ball. Daily at noon, the ships observe the ball being dropped and they set their chronometer to that. So the U.S. Naval Observatory is still an active timekeeper. Obviously, they run GPS, Global Positioning System, Navstar. U.S. Naval Observatory has 59 standard clocks. Think about that. 59 standards. You know, guy with one watch knows exactly what time it is. A guy with two watches, well, he hasn't really got a clue. But what if you got 59 watches? What time is it? Like, oh my gosh. But they do maintain a master clock. The master clock is an amalgamation of those 59 standard clocks. That's what that is. And this is used with the Navstar Global Positioning System, as I mentioned. It was also used with the Loran C, but as we know, Loran C is no longer with us, unfortunately, because it was an extremely accurate source of time and frequency, but it no longer exists, sadly, which I think is Dennis's opinion, big mistake, big mistake. We rely too much on GPS. So let's talk about what came next, National Institute of Standards and Technology. Well, this was established. We know this is National Institute of Standards and Technology today, NIST. It used to be called the National Bureau of Standards. The National Bureau of Standards was founded on March 3rd, 1901. And it was the National Bureau of Standards. And of course, it was renamed, if you've been around and recall that, the change in name in 1988 was when they changed it to NIST. And they're responsible for a lot of different standards, not just time and frequency, but the time and frequency division is what we're interested in tonight. And these guys are charged with maintaining our national standards. Now, our national timekeeping standards from NIST are called NIST F1 and F2, and I'll talk more about these in a little bit. These F1 and F2 are what are referred to as cesium fountain clocks. You've heard of cesium clocks or a cesium beam clock or a cesium beam oscillator. A little bit more on that later, but the cesium fountain, these things are extremely accurate and precise. This is our primary reference for the United States. How about that? 3 parts in 10 to the 16th. That equates to 0.03 nanoseconds per day, or 1 second in roughly 1 second in 100 million years. That's how accurate our national time standard is. That's decent, but they're getting better. We'll talk about that in a minute too. So they're also weights and measures. You know, they're into weights and measures, and they're responsible for testing of clocks and watches. And that was one of their responsibilities back in the day. And in 1904, one of their timekeeping pieces was a thing called a Riefler clock. And that's a photograph of it. And this came from Germany. It's a pendulum clock, but it's a very precision mechanical time standard. And that was replaced in 1929 by something called the short clock, which you see here, which is a double pendulum clock, which is that much more precise than the Riefler clock. But they're still mechanical, still mechanical. This was developed by the Edinburgh Observatory in Great Britain. It was fabricated in London, brought to the States, and it was short-lived. 1929. What happened shortly after 1929? What do we got coming along? Well, We have an electronic revolution is what we've got, the electronic age. Think about this. So we've got radio stations coming up on the air, commercial broadcast. They need accurate time. Radio stations need accurate time. Of course they do. Science was driving for more accurate time all the while. And of course, National Bureau of Standards was heavily into that. The double pendulum clocks were the normal timekeeping piece, precision timekeeping piece at that time. But what comes along next is the quartz oscillator. The hams took advantage of that right away. But quartz oscillators are several orders of magnitude more accurate than those double pendulum clocks. So this provided a reference for timekeeping, not only frequency, but timekeeping. So we divide that quartz oscillator frequency down and get 1 second, 1 pulse per second, or 1 tick per second time for timekeeping, what have you. So that's where that comes from. So this provided a better reference. And I think somewhere coming up here in 1923, the National Bureau of Standards began standard frequency broadcasting time and frequency standard. What's interesting to note to me is that, and of course, we're all familiar with this today. They're still on the air. 1923, we just celebrated a 100th anniversary of that. I just realized that. 1923, 2023, WWV, WWVB, and WWVH are all still on the air, doing those standard frequency and time broadcasts. However, guess what the U.S. Naval Observatory did? They started doing radio broadcasts in 1904. So they were broadcasting time in 1904 from the Naval Observatory. I get a kick out of that. But there you got the roots of WWV. All the time, all the time. So 1929, we've got this quartz frequency standard, and this became now our national primary standard for radio frequency and for time. And it consisted of 4 100 kilohertz oscillators. And you notice that they're in enclosures to maintain the environment, temperature, and humidity, so that they stay at a stable frequency. These were pretty stable for the time, 1 part in 10 to the 7th per month, which is pretty good. It's pretty good at the time, 1 part in 10 to the 7th per month. So as things improved, what happens next? 1949, the first atomic clock. Now, we think of atomic clocks as using cesium as their essential element to make for their oscillations. But the first atomic clock used ammonia, and it was based on the absorption line of ammonia, of an ammonia molecule. And it was a real clock. It counted ticks, which is kind of fascinating to me. But it lasted a couple of years, and that's when the cesium beam oscillator came along. So in 1952, NBS 1, the first cesium beam frequency standard, came about. And this is based on the vibration of cesium, a cesium atom. And it is divided down to provide clock ticks, like 1 pulse per second is what the output of this thing is. And in 1959, this became our national frequency standard, and is also used to drive that national time standard. But a year later, we developed NBS 2. And what's happening on all these developments, NBS 1, NBS 2, and its brethren after that, it's always improving on the accuracy of the clock. So NBS 2 was developed for long-term unattended operation. NBS 1 required a lot of attention. You had to tweak it constantly. NBS 2 was designed so that it didn't have to be tweaked, and it became more the norm. And this was now used to calibrate secondary standards. And we'll talk about the difference between a primary and a secondary standard in a minute as well. We'll talk about different types of standards. So NBS 2, this is actually what we call a primary standard. So here's a picture of NBS 1, and this made it to Ripley's Believe It or Not, the most accurate time machine in the universe. It's even more accurate than the movement of the Earth, believe it or not. That is true. I don't know if you're aware of this, but the Earth's rotation varies quite a bit in time, and kind of surprising. It speeds up and slows down all the time. So September 1953 on Ripley's Believe It or Not. I love that. So the next kind of innovation, and this is kind of fascinating to me. I'm a collector of products from National, what was National Radio Company. National Metal Toy Company became National Radio. National, if you're familiar with the HRO radio receivers, the HROs, that type of thing, they developed the first commercial atomic clock. It was not exactly small, but this was the Atomicron. And in 1958, this was put into basically a commercial product. In my collection of stuff from National, I have an Atomicron, but it's the second generation after this. So it's much smaller. It's a single rack mount unit that's probably maybe it's smaller than a 10.5-inch rack panel. So it's not that big. But that is National is credited with having the first commercial one. When we think of atomic clocks and cesium clocks, we think of Hewlett-Packard. That's who I always think of. Hewlett-Packard, Agilent, whatever they are now, Lightwave Technologies, something like that. But yeah, HP. And we've got several HP cesium beams too here that are kind of fun to play with. But that was in 1958, and it cost $20,000. $20,000 in 1958. I haven't figured that out, what that is. That's probably, boy, in today dollars, it's got to be up in the like $500,000 or more, maybe even closer to $1 million. That was an expensive piece of test equipment back in the day. And this was a cesium beam reference oscillator. This particular one here is the NC 2001 that was built in or manufactured in 1960, and kind of an interesting piece of kit. Here's an illustration of 3 generations. This is actually a quartz oscillator. And I think that's one from General Radio. From what I can tell from the picture, that's a General Radio label. General Radio also from Waltham, Massachusetts. And this is the one from National. And this, I believe, looking at it, this looks like a hydrogen maser, which is another very accurate timepiece that came after these cesium beams. Hydrogen maser. So that's 3 generations of frequency standards right there: quartz crystal, cesium beam, and a hydrogen maser. So let's talk about some of the modern stuff. Let's talk about things like the quartz watch. We're all familiar with quartz watches. They've been around for a while. Well, believe it or not, when we think of quartz watch, we think about Japan, and Japan being the first to produce them. Well, actually they were, but it wasn't invented by the Japanese. It was invented by the Swiss in the 1960s. And they invented the quartz watch, but they're some of the best watchmakers in the world are in Switzerland. And I don't think they were really sure about the quartz watch as they were more certain of their mechanical watches. So they really didn't develop a mass-produced quartz watch until later in the 70s. But the Japanese exploited it with the first commercial wristwatch. And that was the Seiko Quartz Astron. And there it is right there. That is the Seiko Quartz Astron. That was introduced December 25th of 1969. And that really revolutionized personal timekeeping. You don't have to wind your watch. It's not even a self-winding watch. You just change the batteries once a year. So that was a big deal, the quartz watch. So it looks like I'm going back to NIST again to talk a little bit more about the progress there as they develop more and more standards, as they've got more and more accurate. NBS2 in 1960, NBS3 in 1963. We'll visit these again a little bit later. But an important event takes place in 1967. This is the 13th General Conference on Weights and Measures. And at this conference, the second is defined as the vibrations of a cesium atom. So this is a revolution in that we are no longer basing our timekeeping on astronomical events. We're basing it on physics and a cesium atom and the vibrations. And so to this day, the definition of a second is 9,192,631,770 vibrations of a cesium-133 atom. And the official definition is right there as done at the General Conference. It's the transition between two hyperfine levels. So it's that vibration between the hyperfine levels of the ground state of cesium-133 atom. And that is what we define as the second today, and it's to this day. And interesting that that transition from astronomical time to physics. I love that. So here's NIST progressing on. In 1968, they built NBS-4 and NBS-5 in 1972. 1975, NBS-6, and it's accurate to 1 second in 300,000 years. So we're getting better. And look at NIST-7 in 1993. That's not that awfully long ago. But that was 1 part in 5 times 10 to the 15th, or 1 second in 6 million years. That's pretty good. Today, here's F1. This is NIST F1. This is a cesium fountain. And this is accurate to 1 part in 10 to the 15th, or it's 1 second in roughly 30 million years. And they're located, there's additional standards in Germany and in France. And it's hard to explain how this thing works. It's kind of bizarre. The cesium fountain uses a single cesium atom that you see that column there in the center, this thing here. It's lofted into that column, and then it falls, and it's bombarded with a couple of lasers. And by bombarding it with the lasers, it gets super cold. So very little movement. But they are able to basically measure the vibrations of that cesium atom as it falls down through a trap in the column. And so that was the cesium fountain. I was going to include a part, if you've ever wondered how a cesium clock works, how a cesium beam oscillator works, it's really kind of the same principle. It uses it's a what we call the physics package in a cesium beam clock. It's basically a vacuum cylinder that has a cesium beam source, and it goes through a microwave field you want to operate at that exact, the 9 billion whatever vibrations per second. And it comes out the other end of that microwave chamber, that resonant chamber, and it goes into a mass spectrometer. And the mass spectrometer is tuned to that precise frequency, and there's a feedback loop that adjusts the frequency of the microwave oscillator that's driving that cavity that the cesium beam is passing through. And it stabilizes down to where you've got that 133 cesium-133 atom in the mass spectrometer. You precisely measure that. That gives feedback to set the frequency what happens is the beam actually deviates when the frequency changes. So when you've got the right frequency and it's in the right spot, that's when you've got that precise 9 billion and some odd vibrations. And then you can divide that down for whatever you need. 1 tick per second, very easy. So that's how those cesium beams work, using a mass spectrometer and a microwave cavity, a resonant cavity. They're a little bit more complicated than that, but that's the basic gist of it right there. So here's the next one. This is F2. And this is a little bit more accurate, I think. This came online in 2014. It's also a cesium fountain clock, 1 part in 10 to the 16th power, 1 second in 300 million years, which we mentioned earlier. Now, what's in work right now, and I've been reading up about these, NIST F3 and F4 are under evaluation. They're not online yet, but they're being evaluated. And they're basically going to take this hopefully up to the next order of magnitude. And I want to kind of come back and talk about that in a minute too, about there's some profound effects of going to several more orders of magnitude of accuracy than these guys that we've talked about up until now. But let's shift gears and talk about scales of time. This is another aspect of timekeeping. So we talk about, I talked earlier about navigation. So we talk about the sun, the moon, the stars, and an ephemeris. So you use your ephemeris and your sextant looking at the sun, the moon, the stars, along with your chronometer to figure out where you are precisely. The ephemeris gives you all that information. That's what ephemerae are, is the positions of the sun, moon, stars. As you traveled farther, it required more and more precise time. And this is where came the notion of universal time. And universal time was the first based on astronomical time. And we call those UT0, UT1, and UT2. And you kind of see where this goes to what we know today, UTC. This is kind of the progression, UT0, UT1, UT2, UTC, where we are now. But we'll explain these. Universal time. So the first thing we've got is apparent solar time, and that's UT0. That is apparent solar time. This compensates for the Earth's orbit, and it's apparent solar time. So it compensates for the Earth's orbit, and it compensates for the inclination and eccentricity of Earth's orbit. And it uses something called the equation of time. And it adds or subtracts up to 15 minutes by season. Now, the equation of time. When you look at a world globe, you see that little figure 8 illustration that's on the globe, or you'll see that on a world map, the figure 8. That is the equation of time. And that's used to adjust that apparent solar time based on the time of year, and that either adding or subtracting 15 minutes by the season. So the interesting thing of this is astronomers, they use the stars rather than the sun. So we talk about apparent solar time. In astronomy, we use something called sidereal time, which is based on the movement of the stars rather than of the sun, because they don't coincide, as you know. So the Earth doesn't rotate exactly 24 hours, as you know. So as clocks began to get more accurate, they started to show inconsistencies. And this really became a problem in navigation. And those inconsistencies are due to various characteristics of the Earth's rotation and orbit of the sun. So along comes UT1. So the sextant provides your local time. The chronometer provides universal time. And the difference between those two is your longitude. How about that? But due to the Earth's axis varying, we have a lot of variations. The Earth does nutate slightly. We call it the wandering of the poles. The Earth does nutate, which means it kind of wobbles. And so that's going to mess with this if it wobbles. And so we have a wandering of the poles, and this can add or subtract 300 milliseconds per year because of that. So that's what UT1 is designed to compensate for, universal time, number 1. And UT2 compensates for variations in the rotation rate of the Earth. And the Earth does speed up and slow down several milliseconds over the course of a year. And so UT2 compensates for that speeding up and slowing down of the Earth's rotation. And it follows a 1.5-year cycle that compensates UT1. It's just, unfortunately, this one isn't used today. We've got other techniques that we don't need to use UT2 anymore. So UT2 has fallen into disuse. But what do we do today? Well, let's talk about our timescales today. The first thing we talk about is the free atomic scale. And this is maintained. If I could speak French, I could pronounce that, but I'm not even going to try. But suffice to say, it's free atomic scale. This is maintained by BIPM, which is the International Bureau of Weights and Measures in Paris, France. International Bureau of Weights and Measures. There you go. And this is an unsteered, or what we call a free running clock. It's free running. It's not bound to anything. It's computed as a mean time scale between a number of other clocks. It's based on submissions of 200 other time laboratories throughout the world. 200. But as these things got more accurate, they discovered a flaw in EAL, this free atomic scale. What causes the error? And this is interesting. You would think, what's causing the error? The contributing labs introduced variations, and the variations are due to things like altitude. Altitude, gravitational effects, they affect the rate at which a clock, let's say a cesium beam oscillator, oscillates. The latitude that you're at creates relativistic effects. If you're at the equator versus at a high latitude, your velocity is different. If you're at the equator, you're traveling at roughly 1,000 miles per hour. If you're at the pole, you're maybe traveling at 0. And in between, it's a whole range. And as we know, as the clocks have gotten more and more accurate with these atomic clocks, the cesium clocks, the relativistic effects of moving, the motion, the clocks move at a different rate. This is time dilation. And it's very subtle, but if you're looking at it as a very precise measurement of time, this stuff adds up. And one of the things that was interesting a number of years ago, I remember when this experiment was performed. I believe it was NIST took a couple of HP cesium beam clocks, they're beam oscillators. They put one in an airplane and they put one on the ground, and they flew that airplane around for a while, and they brought the two clocks back together, and they were different. So that was kind of a little proof of Einstein's relative, the relativistic effects of time dilation. As you have a difference in speed or difference in velocity, time travels at a different rate, or time moves at a different rate. So this is the relativistic effect we're talking about here. So it started to become a real problem as the clocks got more accurate. So what was needed was a new time scale. Again, if I could speak French, but this is international atomic time, is what it looks like. International atomic time. This is absolute atomic time. We call it TAI. It's a weighted average of those 300 clocks that we did, 200 before, but 300 clocks that are located around the world. We create an average of those 300 clocks, and we create this thing called TAI, and it comes from 50 national laboratories, NIST being one. Of course, it's based on that free atomic time, the EAL, but the inputs have to be adjusted. So we have to have a parameter for each clock that says what latitude it's at, what altitude it is above, mean sea level, right? Because of all the relativistic effects. We talk about inputs are adjusted to Earth's geoid. And as you know, the Earth is not a sphere. It's an oblate spheroid, which means it's fatter at the equator than it is at the poles. Anyway, so all this stuff all contributes. There are other things. Gravity really does affect things. There are gravity actually is not uniform at the Earth's surface. It varies depending on what the underlying material is in the Earth's core, and gravity does vary. There is a variation in that, and that affects things like these national standards. So a determination has been made about all of this stuff. Now, days past, the clocks were actually tossed in an airplane and flown to Paris to do the synchronization. Nowadays, it's all done by satellite. You do time transfer via satellite. But this all leads to an error, and the error in EAL was approximately 10 to the minus 12. So there was a substantial error in EAL compared to these other clocks, this TAI. So all other clocks are coordinated, and there's our universal coordinated time. Universal coordinated time is coordinated to TAI, International Atomic Time. So when you hear UTC, Coordinated Universal Time, it's coordinated with International Atomic Time. And TAI is maintained within 0.9 seconds of UT1. And what's UT1? That's mean solar time, right? So that's based on our Earth's rotation and all of that. So that's where we start, we hear about, we're going to add a leap second. We're going to subtract a leap second this year. That's where this stuff comes from, is from this coordination of TAI with UT1, that mean solar time. So UTC today trails TAI by 37 seconds. And so we've picked up 37 seconds because of changes in the Earth's rotation, changes in the orbit of the Earth. All of these things have all contributed, because remember that TAI is an absolute. free running scale. But what good is that if it's always wrong? It is wrong. So UTC is corrected, coordinated, so that we always have the right time, so that the sun rises at the right time and the sun sets at the right time, and we add and subtract leap seconds to make that happen. And that international standard, now maintained by BIPM, the International Bureau of Weights and Measures, is UTC, and it's TAI with the leap seconds applied. And so everybody else synchronizes to that, including NIST. I mean, NIST, they may be a primary standard, but they synchronize their primary standard to BIPM and UTC. So that's probably more than you ever wanted to know. But the other thing that's interesting about all this is that there's actually two time standards in this country. We've got NIST, National Institute of Standards and Technology, and we've got the U.S. Naval Observatory. And of course, what kind of conundrum does this cause? We'll get there. Okay, we'll talk about some other scales. Let's talk about the U.S. Naval Observatory. I get a kick out of this one. So GPS, we all think GPS is a miracle of our modern age. I mean, GPS is fantastic. We probably rely on it way too much. But the first epoch of GPS began on the 6th of 6th of January 1980. That's the first epoch. GPS does not add or subtract leap seconds. It's another absolute time. Ooh, I wonder if that's correct. I didn't check this today. I didn't check this number. At the time I made this presentation before, it was 19 seconds. It probably does lead, because it does change year after year. It does change. But GPS time actually leads UTC by a certain time, that leap time. And what happens if you're using a GPS receiver, the GPS receiver gets the absolute time from the GPS constellation and adds those seconds in. That's how it gets your correct time. So your GPS receiver takes care of all that stuff. But these clocks are maintained by the U.S. Naval Observatory. Hence, I mentioned that it's another time standard, two time standards in this country. But we consider our national standard to be NIST. And by definition, U.S. Naval Observatory time is not traced to NIST. So if we talk about tracing standards, if we're making measurements and we want to check the accuracy of our standard that we're using, we trace that standard to NIST. So if I've got a clock, I can trace that time to NIST. Well, if NIST is our national standard, but U.S. Naval Observatory is not traceable to NIST, how do we maintain that? Well, it turns out that NIST monitors the GPS constellation and measures the deviation from F1 and F2 from the GPS constellation. And they track that data, they archive it, and they publish it daily. So if I want to know what time it is right now, a traceable time, traceable to NIST, I have to wait 24 hours. I got to wait till tomorrow to download that table with all of that information in it. I'm going to share the, let's see, I got to get rid of my laser pointer, turn that off, and then I can go do this. I'll pull up, it's probably not going to, that doesn't show up, does it? You're not seeing, are you seeing this, Dan? Or are you still seeing the PowerPoint?
You'll see the PowerPoint.
Okay. I was going to bring up the website, NIST's website, so you can see that, but I don't want to drop my presentation to do that. So we'll keep going here. But this link that's here, this link takes you to the NIST page where you enter the date that you want to have you want to get the variations of time on GPS. You can get that any date. I actually don't know how far back it goes. It might go back quite a ways to the first epoch. I don't know. I've never looked at that. That'd be something to check out. But that's how you have to trace it yourself. In other words, you can't use, if you're claiming that your time that you're getting from GPS is traced to NIST, it isn't. You have to do the math. You have to go get the tables from NIST, do the calculations, and you have to do it 24 hours after it occurred. They publish it every day. So kind of a crazy little thing. But they do publish that results the following day. So there is still, there obviously we talk about these variations in the time, and it leads to a certain uncertainty. And one of the things that came out of the showing you these different time standards with NIST is how that uncertainty has changed over the years. So back in the 50s with NBS1, we're looking at like 1 part in 10 to the minus 10, or 1 part in 10 to the 10. Now F1, we're looking at 1 part in 10 to the 15th. And that's as of, at NIST F1, F2 as of 2010. This chart's kind of old. It's gotten a little bit better now. But I got to tell you, one of the things, as this is a fairly linear scale here, fairly linear. If you extrapolate this thing out here to, let's say, 2020, one of the problems when you get that accurate is that if you would move the clock, if you pick the clock up and move it, take it upstairs, it's not going to be the same, because gravity, you have gravitational effects, you move the thing. So there's velocity involved in that. All these relativistic effects affect the time. So when you start getting out to this 10 to the 1 part in 10 to the 18th, you got some serious issues. I mean, probably just vibrations of the ground will affect it. So there's going to be some interesting things in the future as they try to get these things more and more accurate. But I love this scale. It's an uncertainty in nanoseconds per day, 10,000 nanoseconds per day, down to where we are today, like 1 nanosecond, or a fraction of a nanosecond per day at our time. So as you know, NIST does some other stuff. We talked about WWV. So they've got the time and frequency transmissions, and that's a picture of some of their equipment. And that's Fort Collins. That's the transmitting site. What you can see in this rack here, these are the Hewlett-Packard 5061 cesium beam standards, and that's what they use for the frequency standards. That's what they use to develop their frequency. And the time comes from F1 and F2, but the frequency comes from those guys right there. Those are considered primary standards. I'm trying to figure out those. I'm not sure what those transmitters are. I don't know who those were made by. They almost look like Technical Materials Corporation, but I'm not sure about that. But anyway, that's what NIST is up to there. That's if you've ever wondered what goes on at WWV, there's the transmitter, and there's some of the frequency standards. So I mentioned before about primary and secondary standards. So when we talk about primary standards, these primary standards are something that you can set and forget. You use that as your primary standard. And a cesium beam standard is considered a primary standard. But I mentioned earlier hydrogen maser. A hydrogen maser is actually a commercial product, rather pricey, but a hydrogen maser is 1 part in 10 to the 15 or better for short periods. Okay, they are very, very accurate. The cesium beam, like a 5061 or a 5071, I've got 3 5061s. They're, like I said, they're fun to play with. They're accurate. If you use that to drive a clock, they're accurate at 1 second, 300,000 years. That's about what it equates to. But we'll talk about secondary standards. Secondary standards are something that you might have, like I considered like a Loran-C comparator, but can't do that anymore. Yeah, I have several Loran-C receivers that are used to get standard time and frequency. They're useless now, unfortunately, but they were fairly accurate. They're considered secondary standards. GPS time and frequency references are considered a secondary standard. They actually use rubidium oscillators on the GPS spacecraft, and rubidium oscillators are a secondary standard. They do drift. They have a real advantage over a cesium oscillator. Cesium oscillators are noisy. Rubidium oscillators are very quiet. Now, there's not a lot of noise on the signal they generate. So for short periods of time, they're extremely accurate. And typically when they use these, use the rubidiums, they will allow them to what they call freewheel. In other words, it'll just freewheel for a short period of time. and then you discipline that rubidium oscillator back to your standard, and then you let it freewheel again because it's very quiet when it's freewheeling. So you don't introduce a lot of noise into your system. But those rubidium standards, there's what you're looking at with that 1 part in 10 to the 11th, 1 microsecond per day from rubidium standard that you could hold in your hand basically. You can use a WWV comparator, and I've talked about those before when I talked about radio astronomy. We use a WWVB comparator to determine frequency. That's again 1 part in 10 to the 11th, so it's pretty darn accurate. But compare that to like an ovenized quartz oscillator, which a lot of you may be familiar with. We know about ovenized oscillators. We know about temperature compensated TCXOs, temperature compensated crystal oscillators. You can see where the comparator is a lot more accurate than the ovenized oscillators or the temperature compensated oscillators. So 10e to the 1 part in 10 to the 7th for a temperature compensated quartz oscillator. And of course, a good old plain quartz crystal, 1 part in 10 to the 6th. Yikes. So did you ever wonder about the first atomic watch? You know, they talk about atomic watches all the time. You know, you can get an atomic watch on your wrist. Well, they're not really. Those are WWVB receivers that are receiving a signal from an atomic clock. But how about this one? I love this guy. There's the world's first atomic wristwatch. Hewlett Packard 6071 cesium beam oscillator. Yikes. He's got to have a long extension cord. But seriously, the atomic clocks, as you know, these are so common today. We don't even think about them, but they synchronize daily with WWVB on 60 kilohertz. And they maintain an accuracy of about 1 second per day, which for what we do, you know, that's probably more than accurate enough. They're not really atomic clocks. They just synchronize to one. But look to the future. NIST is actually working on several interesting things. They're working on an optical clock that's 3 orders of magnitude better than F1. And remember my comment about moving? Yeah, move it, take it upstairs, bump into it. It's going to use a mercury fountain, and it operates at a frequency 100,000 times higher than the cesium vibration, the 9 gigahertz range. So this is really high frequency. But again, the relativistic and gravitational effects, this is really going to mess with that. And NIST is working on things they call an optical lattice clock that uses other exotic materials like ytterbium and strontium, such like the mercury. And these will be 100 times more stable than NIST F1. So we're getting crazy in the future, and we keep our eyes open for these. These will be our next standards. But one other thing that I really get a kick out of is NIST has been working on something else, which is a sub-miniature cesium clock. And that's the physics package right there. That is the cesium beam. And you can tell that that's pretty small. The idea is to put a cesium beam device on a chip. And if that happens, you got a cesium beam wristwatch. And I think that'll be really cool. It's not as accurate as a full-scale cesium beam, but it'll be pretty darn accurate. And it will be probably the most accurate watch you could ever own, even more accurate than the atomic watches. So this begs the question. And I don't know, I haven't been watching the chat. I should have been watching the chat because somebody may have yeah, that's true. I don't know if there's any other. So nobody asked the question. Nobody asked the question. So what time is it? And I like to say, well, it depends. What are you doing? What's your application? You know, are you doing navigation? Are you trying to get across the Pacific Ocean? Are you launching satellites or landing on Titan? Are you doing astronomy or other scientific adventures? Are you just trying to get to the office on time? Or are you trying to run FT8 or play with the Oscar satellites? That's where it really matters. And So it really depends on the application. And like I said, if you really want to know what time it is right now, this instant, I can't tell you because I got to wait 24 hours to get the results from NIST of the GPS that I have my clock back there synchronized to GPS. What can you do? So I don't know if that's accurate or not until tomorrow. Then I'll know it's accurate. But that's it. There we go. And I will end the slideshow and return this channel to normal viewing. And I see we have a hand up, and let's see.
Okay, Victor, take it away, sir.
Go ahead.
Well, thank you and good evening from beautiful downtown Everett, Washington, where we've got a flood stage going on, and we're
Oh no.
by cubic feet per second. I think it's cubic feet per second, something along that line. You mentioned early about Loran C, and I know Loran is the definition of long range navigation for ships on the ocean. And
Well,
part of that, and it evolves into a question, is what happened to Loran. But when we start talking about precision, I remember the space program, and at launch time, they would announce the launch was 671 thousandths of a second late. Now, that's a huge calculation by the time you get out to the moon, and if you don't correct for that mid-course, you're not coming back. When we start getting into smaller and more precise timekeeping, that's going to become critical when we decide we want to land a ship on Pluto.
well, we're already doing that. I mean, we're already out there doing stuff. Sorry.
Have a great week.
You know, you think about things like JPL and other laboratories around the world that are doing deep space probes. We're already there. I mean, you're talking about navigating a satellite that's billions and or spacecraft that's billions and billions of miles out in space, and trying to go into not necessarily going into orbit, but you're trying to have a trajectory that skids past some planet, let's say Neptune or Uranus. And I'm blessed with having one of my friends worked at JPL and actually flew the Voyager spacecraft. He actually flew the spacecraft. He was in the operations center there. And one of the things that he told me is that when Voyager, I don't remember if it was Voyager 1 or Voyager 2, but when they went past Neptune, that spacecraft went through basically a target that was 15 miles square. And that 15 miles and so that takes things like precision time and knowing the distance, knowing the velocity of the spacecraft, all of these things, and it requires extremely precise time. And another friend of mine back in the day was responsible for with JPL and the Deep Space Network setting up the first cesium atomic clocks that they use for JPL for the Deep Space Network to synchronize the stations. So yeah, they've been doing that. They have to do that, and it's going to get more and more precise. You know, you think about, we launch a spacecraft and we land it on Mars, and we have to deal with all the time lag. You know, the time that it takes for signals to transverse back and forth. So we have to know precisely where it is, and the only way you know precisely where it is by knowing precisely what time it is. And of course, the spacecraft itself has navigational features on it, or systems, you know, or what do they call it? Basically uses a star as a guidance point. So they're getting data from that to know where the spacecraft is, but it really takes precise time to do those things. And you know, your GPS receiver isn't going to cut it. Let's just put it that way. But yeah, good point. It is a good point. And we're just going to need more and more accurate time with less and less variation. It's just going to get harder and harder all the time. Oh, you're muted. If you had another comment, or was there another comment? You muted yourself, Victor.
Yeah, I just said 15 miles. I mean, That's not a lot of real estate.
No, it isn't. It's very, very small.
But what about Loran?
Oh, Loran.
Would Loran see a timepiece, or was that just part of the long range navigation?
Oh, it was actually both. You had frequency and time, and Loran C operated at 100 kilohertz. And pardon me, Loran C could be used for navigation really anywhere. Loran C, Loran goes back much, much farther. And the typical Loran receivers of the early days were monsters, big, floor crushing receivers. But the Loran C receivers were quite compact and could be handheld. GPS superseded that, obviously. But Loran C can be used on land. It can be used at sea. You could probably even use it in an airplane if you wanted to, if you had a system to receive it. And I used it for timekeeping is what I used it for before I put up a GPS receiver. I used Loran C for time, and you have to compensate for your distance from the Loran station, but it's actually more accurate than the time coming from the frequency coming from WWV. Let me put it that way. And you use a frequency comparator to look at the Loran signal, and if you know your distance from the station, you can figure out the propagation time and compensate that propagation time into your time based on what you're receiving from their signal. So if it takes 100 microseconds for the signal to get to you, that's probably too small, but let's say 100 microseconds. That means that if you set your time to what they're saying at that point, you're 100 microseconds behind. So you advance your clock 100 microseconds to compensate for that. It's all ground wave, except at night. It becomes a sky wave. And that's called diurnal. That's the diurnal effect of day to night between the ground wave at low frequencies during the day and the sky wave during the night at low frequencies. And that changes the length of the propagation path. And so you use a comparator to measure that difference. And you can compensate your clock. And this is when I first got into this stuff. This is what we were doing at satellite control facilities where we're actually flying satellites. We'd actually measure the times, basically a time signal coming from something like WWVB, the low frequency one, and run that through a comparator and use that to tweak the rubidiums that we had at that site to maintain accurate time. Boy, we've really run over, haven't we, Dan? I'm looking at the time.
I think we're doing okay.
We're doing okay. All right.
It's a good program. I was in the Navy. Oops, where did I go? I was in the Navy in the 60s and 70s, and the military out to sea, our crypto system was based on time. And if you were off a fraction of a second, it chopped all your crypto cards.
Well, yeah, that has to be synchronized. Yeah.
Good.
Yeah,
I don't know how to raise my hand, so can I talk
okay,
a
go
minute?
ahead. Go right ahead.
Go ahead, John.
Yeah, I was just going to say, and I realize I don't know how long these things usually go. When I was in the Air Force and I worked in the PMEL labs, used to calibrate time bases, and we used Loran C with a fluke. I don't remember the name of the receiver with a paper chart on it. You probably know the one. But I've got to tell you a story. One time I was in Boulder, and I'm driving down the street. I work for Union Pacific, and I was at Denver over the weekend, so I was just cruising around. And here's this building with antennas bristling out of it, and I think, what in the world is this? So I go in there, and they're open.
Oh, yeah.
And it was NIST, and so I go, oh, well, I don't know all about it, but I know a lot about, frequency standards. So I'm going to go back down the hall. Have you ever been there?
I've never been there.
Big long hall, and the first thing you see is these Air Force guys working on sunspots and the solar radiation and God knows what. And then pretty soon you get down the hall, and there's this, it says, I don't remember what the number was, 6 or 7 in there. It wouldn't have been 7. What's the name of those clocks again? And
like NIST 1, 2, 3, 4,
yeah,
5, 6, 7.
NIST. It was probably 6 or 5 that was in there at the
Uh-huh.
time. And the room is completely dark, and there's no lights, no nothing except maybe a couple of panel lights on something. And I've got my head up to the glass looking in because there's light in the hall, and I'm thinking, well, this is weird. They don't have this thing turned on.
Oh, no.
Well, so by chance, there was 3 guys that came in the back door and walked around this thing and came out in the hall. And me being kind of a smart ass, I said to them, how the hell do you tell time around here with the Timex? And this guy jumped about 10 feet up in the air. And then once he knew I was in the PML business, he says, oh, well, I'll show you how this works. So we went in the other side of the building, and there was a rack, just a plain old sort of rack, but it was insulated. And they had 3 different, they had a Hewlett Packard clock, a Roden Schwartz clock, and maybe something made in Japan, I don't know, another. And they didn't use the main device, NIST or whatever, number 7 wasn't even on. The only time they turned it on was twice a year to sort of synchronize, if you will, or see if things are still in there, and or if one of these 3 clocks came on, got a little bit off whack, then they turn it on and see what's going on. So I'll shut up because I know we got to go. But
that's cool.
And they were building the last one. I think it was number 7 that was right there. I mean, I touched it. It's just a big, huge stainless steel pipe, right? But
yeah, that's right. Yeah, yeah. That's sure.
So, by being a smart ass and saying, how do you tell time around here with a Timex? And this guy, well, anyway, so it goes. So that made my day. I really got, and it's been unfortunate. I've never been able to get into a WWV transmitter site.
Yeah,
course,
that's going up. That's up at Fort Collins. Yeah, Boulder. Their headquarters is still in Boulder, but the transmitting site's up in Fort Collins.
Well, the clock, the fountain thing, and now is that I don't know if they must have that built on a big slab of cement or something.
Oh, so I'm sure it is. It's on some kind of, and it's of course environmentally controlled, precise temperature, and you open the door and it's off.
No, they use a Timex. Okay, here we go. Exactly. Bye bye.
Takes ticking and keeps on ticking.
I'm going to jump in the middle of this conversation.
Yeah, go right ahead.
John, I appreciate your story. It was great.
Yeah.
Join us more often. You don't join us very often. You're welcome to do it. And back to you there, Dennis.
Oh yeah, that's right. Yeah, look at comment from Dave. Right on. Yeah, with the near. That's cool that you were part of that. That was a neat program. Yeah, oscillator drift on the spacecraft. Yeah, because the temperature and all of that, 30 milliseconds a day. Yes, that is too much to correctly manage navigation. So you're somehow adjusting that time. I mean, that's what really happens with the GPS satellites is that NIST makes their measurements and USNO gets the data and they have to tweak the spacecraft to keep them on the correct time. Keep the correct rate. It's really the rate, the variations in the rate of oscillation of those rubidium oscillators on the spacecraft. So
I don't see any more hands up.
I don't see any more hands up either, and no more comments.
Yeah, this has been a good presentation.
A little different.
All right. Well, with that in mind, we are going over, which is fine.
Yeah.
Great presentation. Appreciate you doing that, Dennis.
No problem. My pleasure. Enjoy it.
And I'm with Steve Waterman. I says, we're going to have to make a raid on your shack someday.
Uh-oh. Oh, if you're interested, those folks that are still here, if you want to learn some interesting stuff about timekeeping, there's a group called Time Nuts. And I haven't checked to see if they probably moved over to groups.io. I used to subscribe to that when they were on the old I think they were on, I want to say they were on Usenet and then Yahoo Groups, but Time Nuts, and I think it's with the Z, Nuts. And these people take it to the extreme. You know, I'm extreme enough having a couple of HP cesium beams, and I've got them because I was able to get them, and they were inexpensive. But they're a pain in the neck to maintain. They consume the cesium. So what you do is it's got a quartz, like kind of like what John, what you were talking about, the cesium beam oscillator HP, like the 5061s that I have a ovenized quartz oscillator. It's like a double oven quartz oscillator. So it's pretty accurate quartz oscillator. And it's disciplined by the there you go. Thank you, Dave. That's it. It is NUTS. Yeah. It's disciplined by the cesium, but what you do is because the cesium is consumed, you don't want the thing to die on you. So you turn the thing on about once every 6 months and let it warm up and let it lock. And then it disciplines the quartz oscillator. And then you turn off the cesium beam oscillator and let the quartz oscillator run. And you let it run for another 6 months or however long, and then you reset it again. So it's a disciplined quartz oscillator is what you're actually getting your 1 pulse per second from. And the frequency standards come from that quartz oscillator rather than from the actual cesium beam. And the cesium beam oscillator is used to discipline the quartz oscillator. Anyway,
okay, Liz will be here now.
Sorry?
Oh, Liz. All right, we're running long on time. Do you have any more hands up or questions in chat?
I was going to make one other comment. I've got a rubidium standard that I got by accident.
Uh-oh.
And I use my HP 5245L, which was a terrific machine in its day. Something went wrong with the quartz in it.
Oh.
And one day I go in there and I'm measuring something. I said, well, this is nuts. I'm off 3 or 4 kilohertz. I mean, what the heck? Well, anyway, I got this little U-block chip, and you can tell those to put out any frequency you want, and they lock to the GPS constellation. And so I'm locked on, and I love it when I can put my rubidium standard into the input and the GPS not disciplined, just coming out of the chip, and get 8 zeros and a 1 that's off scale on a 10-second count.
That's cool. That is
so
cool.
It's a slick system, I tell you.
The rubidiums are extremely good for short periods of time. And that's why they have to be disciplined.
I guess they used tons of those with cell phones in the past, but I guess that's kind of gone out the window or something.
What the cell sites, one of the things about the phone system is that the trunking between, or the links between cell sites, between all your switches and all that, are synchronous. And they have to maintain that synchronism between them. And it was done originally by using cesium beam standards. Cesium beam standards, the phone companies used thousands of those things, and they became available cheap when they retrofit them to GPS. So all the and then nowadays, I don't.
You mean rubidium?
No, not rubidium. Now they're using the cell sites. Well, the cell sites are using GPS and using GPS to discipline a rubidium oscillator, probably, instead of using the old cesiums that they had before. So that's how I got my cesiums. They came out of cell sites that were, from the phone company. And the rubidium is a secondary standard, so they do drift, and that's what you have to be aware of. They do have to be adjusted, and that's where the GPS disciplining the rubidium oscillator comes in. I use I've got a couple of they're good old Ball Aerospace M100 rubidium oscillators. They were basically for avionics. They would fly these things, and you could hold it in your hand. It's a little rubidium oscillator.
Yeah, they're like one of those CubeSat things, right?
Well, no, but they're
not a CubeSat, but they're about the same size. They're about
fairly small,
6 inches square.
About 4 inches square. Yeah.
I've got to tell you, your clock on the wall coming through the the network here
Yeah, there's some
is
delay.
what almost the delay going through whatever this is Zoom
Yeah,
is almost dead on 1 second delay.
really.
When that thing clicks, I mean, it's just really accurate. When you
darn.
click, when it the WWV, which I could turn on right now,
That's okay.
goes tick, 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 time at, and it goes bleep. Yours is reading 59 seconds exactly. And I know your clock isn't wrong, but that's just it. Okay, I'm wasting too much time on nonsense. 70.
We got
It's great, John. We appreciate your comments. Thank you.
Yes, thank you very much, John. Have to have you on here more often.
Yeah.
Thank
There's
you.
another comment and chats there with a link. And
Yeah, I used to be on the mailing list there. Yeah, I used to be on their old mailing list years ago. Fibo.com is the one I remember. That's great. Yeah,
okay.
that's great stuff on that on their website.
Thank you for wrapping this up.
Yeah.
And say
Thank you, everybody.
Great time, good time. Right on time.
What
I
the
enjoyed
heck time is it? Over.
All right. 73s, everyone. See you tomorrow.